Okay, good morning, chemistry students. I'm the only one home right now at this point, and so I really want to finish this module up so that you can move on. And so I'm going to try to do this. If it doesn't work, when Carolyn gets home, I will start over. But I'm wanting to get finished because we need to move into you need to be able to take the test to move to the next module. So we have a few problems or types of problems left, and so let's get started. We are going to start on extra practice problem number 8. So turn to page 215. I am going to see how I can video, write, talk, teach, and all that together, and we will see how this works. Okay, so our problem says a decomposition of 200.0 grams of a dark green powder yields 79.4 grams of potassium, 55.8 grams of Mn, and an unknown amount of oxygen. What is the empirical formula? Okay, so we've learned about decomposition, and we know that in a decomposition we have the original compound. I can't get the lid off my marker, sorry. We have the original compound that is broken down into its elements. So what are the elements that make up this compound? Okay, think about it. It tells us, okay? So we know we're going to have potassium plus Mn plus oxygen. What do I have to do to oxygen? There must be a 2. Why? It's a homonuclear diatomic. That is going to be extremely important for you to get this problem correct. You have to memorize those things. Okay, since we know it's a decomposition, we know that the compound itself consists of those things. Okay, so we are going to put that. So we know that our compound contains potassium. We don't know how much. Okay, we know it contains Mn. We don't know how much. We're giving it algebraic coefficients there, okay, and O, and we don't know how much. Okay, so at this point, we have the problem. And so what we're going to do is to be able to figure out these, we need to come up with a balanced equation. And we can do that over here by figuring out the stoichiometric coefficients. Okay, in other words, what goes in front of these? And I did not leave enough room for this problem. I'll have to fix that as we're going. Okay, so what do we have to do to get it into stoichiometry? We've got to figure out the moles. Okay, so let's look at the rest of the information that we have. Okay, so we know from our problem, I always like to write my stuff on top so that I know where everything is and I can keep up with everything. Okay, we have 200.0 grams of this dark green powder. Okay, and then we also have 79.4 grams of the potassium, and we have 55.8 grams of Mn. Okay, now it says we don't know how much oxygen we have. Well, so how could we figure that out? Well, if we know that we have 200 on this side, what do we know? Now this is with grams, not with moles, okay? But just like we learned the law that said this side must equal this side. And working with Bo yesterday, I should have looked this up, Bo. I didn't look it up. Law of mass conservation, I think is what I'm going to go with. That's what he said. I should have looked it up to remind myself. Okay, so it must equal 200. So we can figure this out by adding 79.4 and 55.8 and then subtracting that from 200. Okay, and so I'll just write that. I'm just going to write, okay, so we have 200.0 minus 79.4 minus 55.8. We have 64.8 grams. Okay, so now at this point we know how many grams it is to create this, okay? But that's not what the question's asking us. It is asking us what the empirical formula is, and that means we have to figure out what these are. Okay, so let's continue from there. So what do you have to do? What do you have to do to figure this out? Well, you need to get each of these into moles, and how do we do that? Hopefully you're answering these questions in your head as I ask them. Okay, well, we have got to, we know, how can we relate to grams and moles? We know that for each element, the atomic weight, 1 mole equals the atomic weight of that element. So let's do each of the 3 elements. Okay, so looking at potassium. Okay, so I have 79.4 grams of potassium. Okay, now, how much is 1 mole of potassium? Okay, look at your periodic chart. You should be able to know by looking at that. I'm sorry, I wrote that in the wrong place. Okay, 1 mole here. Remember, they always have to be opposite of each other, and it is 39.1 grams. Okay, I made sure these are opposite of each other. Okay, so what is my mole for potassium? I have to have 3 significant figures, so my answer is 2.03 moles of potassium. Okay, now I'm going to go up here in the spot that I did not leave. Sorry about that. 2.03. That is my coefficient in moles of potassium that we have in this problem. Okay, I'm going to do the same thing with Mn and O2. Now think about O2 may be a little bit different. Kind of be thinking in your head already what that's going to be. I have 55.8 grams of Mn. Okay, and how much is 1 mole of Mn? Look at your periodic table. It is 54.9 grams. Again, I need 3 significant figures. So I have 1.02 moles of Mn. Okay, I'm going to go up here and I'm going to put it as my stoichiometric coefficient. Okay, 1.02. Okay, now I need to do oxygen. I have 64.8 grams of oxygen. Oops, why am I writing 16? I don't know. Okay, 64.8 grams of oxygen. Okay, now with all the rest of these, I didn't write anything out. Okay, but let me remind you, on your homonuclear diatomics, oxygen never stands alone in a problem by itself. Neither does hydrogen. It can be alone when it's inside a compound, but by itself, because of the number of valence electrons, it doesn't stand by itself. So there are always 2. So is there ever going to be the weight of just 1 oxygen? No. Okay, so when I come up with the atomic weight, okay, I would do, what is the mass of O2? Well, I would have to write 2 times 16, okay? So it is going to be 32. Don't let this throw you, okay? So over here, 1 mole is going to be 32, oops, sorry, I'm not even focused on it, 0.0 grams, okay? Again, I need 3 significant figures, and so I have 2.03 moles of oxygen. And so I'm going to write that up here. Sorry, I know this is awful. Sorry, guys. Okay, and the writing's even worse. Okay, so at this point, you know, you look at it, what's wrong with this? Well, we don't usually do stoichiometric things with decimals, okay? So I think the books called it a wrinkle. This is a wrinkle, okay? So what can we do to fix this? Well, and I wrote this down in my notes. I want you to all probably do this. You will divide by the lowest number so that you end up with whole numbers, okay? Make a note. Divide by the lowest number. Let's look at our 3 numbers. We have 2.03, 1.02, and 2.03. What is your smallest number? It's 1.02. Let's divide all of these by 1.02. Okay, so now I'm going to divide, and I've already done all this, so I'm not doing it. I'm just going through it with you. 2.03 divided by 1.2, you are going to get 2. Okay, so we have 2 potassiums. Plus, and obviously this will be 1, we just have 1 Mn, plus again, we have 2. So we have 2O2. Okay, now that we've done all of this, we can come up with our empirical formula, okay? So we have K. How many potassiums do we have? We have 2. This has to balance, so a 2 would go here. Okay, Mn. How many Mn's do we have? We have 1, so I don't need to put anything there, okay? And then what about O? How many O's do we have? We have 4. This is our empirical formula, and this would be your answer, okay? K2MnO4, okay? So there's that problem. If you would like to do some more problems like this, you can do, sorry, I'm trying to read my notes, on your own, 8.11, or practice problems 9 and 10. Feel free to go over those and then call me or whatever. Okay, now let's go over to extra practice problem number 10. Okay, and we're going to figure this one out together. Let me erase all this. Okay, sorry. Okay, so in our problem we have a compound has an empirical formula of CH2O, okay? CH2O, okay? If its molecular mass is 60.0 ammus, what is its molecular formula? Okay, how would you solve this? Okay, remember, this is the empirical formula. This is to its lowest possible way. But it could be C2H4O2 or C5H10O5. It could be all of those things. So we're going to figure out when this one was done with this empirical formula, and this is the weight. What is the molecular formula for that? Okay, so how do we figure that out, guys? Okay, let's come up with the mass of CH2. CH2O. Okay, and so we figure that up by 1 carbon is 12.0 plus, I'm not getting far enough back, sorry. I know this looks awful. 2 times 1.01 plus 1 oxygen is 16. And so it is 30.0 ammus. Okay, so this empirical formula weighs 30.0. But the compound that we're looking at weighs 60. How can we figure out what the molecular formula would be? Well, we're going to take the amount of the compound, 60.0 ammus, and we're going to divide by what the empirical formula is, 30.0 ammus. Okay, we're going to divide that, and we're going to get 2.00. The gist of this is it's like a double recipe. I've cooked something, and this compound is a double recipe. Okay, so I go through to make the molecular formula, and I multiply it times 2. So my answer is going to be C2H4O2. Okay. I multiplied it by 2. I took my empirical formula and I doubled it all. Okay, that's how you do that problem. Okay, if you'd like to do some more like that on your own, 8.10 and practice problem 8. Okay, so I have one more that I'd like us to go over. Turn over to your study guide. I got to get there too. Okay, and look at number 3. Okay, so with number 3, we have a chemist experiments with this following reaction. This is going to be a super long video. I'm trying not to mess this one up. Okay. It's 14HCl plus K2Cr2O7 creates 2KCl plus 2CrCl3 plus 3Cl2 plus 7H2O. I have to get that written in a second. Okay, if he adds 15 moles of HCl to 1 mole of K2Cr2O7, what is the limiting reactant? Okay, so remember, think in your mind, what is a limiting reactant? Remember, we learned that's the thing that determines how much product there is. That's the thing sorry, I can't write and think at the same time. That limits, okay? Sorry, that's not gonna all fit. Okay, so with this, okay, the question is, if he adds 15 of this to 1 of this, what is the limiting reactant? Well, you should be able to look. Let's relate. We can relate these things in moles. That's how we relate. We know there are 14 moles of HCl equal to 1 mole of K2Cr2O7. Okay, so if he puts 15 moles of HCl and 1 mole of K2Cr07, what is going to be the limiting reactant? What's he going to run out of first? Well, he's going to run out of this first, okay? But because he's going to have 1 mole of HCl left over. So the limiting, this is the limiting reactant. I'm going to write LR, okay? So the K2Cr2O7 is your limiting reactant, okay? You're going to have a problem kind of like that. Okay, now, but let me ask you another question that goes with this, because you have a problem kind of like this. Well, with the reactions and the quantities that were given, how many moles of KCl would be formed? Okay. Well, the stoichiometry doesn't change. Okay, remember with the example of if we had 2 car bodies and we had 9 wheels, we still can only create 2 bodies, two completed cars. Okay, that's the same thing. Even if you had 15 HCLs and you only had 1 of these, okay, everything relates here. You would only create 2 KCl. You would only create 3 Cl2 and 7 H2O. So the question asks, how many moles of KCl would be formed? The answer is 2. That does not change. Okay, hopefully, guys, I have covered everything. Really, the only other thing, remember that when you are doing stoichiometry, it is in moles, not grams. You cannot relate across here in grams. You would have to change it, okay? So just remember that. That's kind of another question. And I think we are finished. Thank y'all so much for watching and participating. Okay, bye.